Okay, again, sorry I'm late. I will get the folders out to you very soon. So today is our last day of new material before the test. So today we talk about using tables of integrals. Coming up on Friday is our review day for test number 1. I have no formal agenda for that Friday. So it's basically just like work on practice problems or work on old homework or whatever you want to do to help you prepare for the test. One thing that I don't want to see people doing during class time on Friday is the project. So project 3 is due on Friday. Throw it in the folder at the start of class if you have it. If not, you can wait until after class and try to finish it up outside of class, okay? But I don't want people working on the project during class time. Any questions on the plan? I will get the homework folders. Okay. All right, so we're on page 79. We'll start up here at the top. So, daily summary. In this class, we learn how to use a table of integrals, which sometimes involves doing some transformation on the original integral to put it in a recognizable form. So today we're going to use a lot of magical formulas that some of which we already have the tools to kind of understand, and some of them we don't yet have those tools. But that's okay. We'll just try to use the table as best we can for right now. Number 1 says on the inside back cover of your textbook, you will find a collection of about 30 integration formulas. I scanned that and I put it in the packet, so go find it. It should be like the first page or 2, depending on how many attempts you had on quiz number 2. Table of integrals, rip that page off. We're going to use it today. What page is it? 7? Page 7, rip off page 7. Everybody find it? Ripped it off? Okay, so let's jump in and see if we can't use the table of integrals to tackle some tough integrals. So, number 2, part A, x to the 5th ln of x to the 5th times ln of x. So we are looking for one of these formulas on this page that looks something like this guy here. Now, I think there's a front and back, right? Is there a front and back? Front and back. So, to help you, this is probably the first time you're looking at this table. What you'll want to do first is recognize the bold titles that are at the top of each section. So the top section is these differentiation formulas, right? And then we got the short table. So you got your basic functions, and then we've got some products of e's and cosines and sines. What we're looking for right now is this x to the 5th times ln. Does that seem like products of e's and cosines and sines? No, so we're moving on. Products of polynomials with ln, e, cosine, or sine. What do we think about that? That sounds pretty good. And so now we've got a good sense of like where roughly we should be looking. So I see 13, 14, and maybe 15 and 16 on the next page. So what number do you think? 13 is good. This is a formula for x to the n times ln of x dx. Formula number 13. How much is n in our problem? 5. And so it's a simple matter of just copying the right-hand side of that formula, changing all those n's to 5, and moving on with our lives. You just stopped coming to class if I gave this to you before. No, I did. I gave it out on the first day. Okay, so this is formula 13. I don't have it in front of me, so can somebody tell me what the answer is here? Okay, so 1/6. Can somebody confirm that? Last one should be x to the 6th. Okay. Any questions on how to use that formula? All right, so they'll get harder than this for us today, but pretty straightforward, right? If the formula happens to just match one of the things that's in your table, then you just plug and chug and you're done. Okay, next one. 1 over cosine cubed of x. Again, don't read every single one of these formulas. Read the stuff that's in bold. So, looking for, what was it, 1 over cosine cubed? Okay, 1 over cosine cubed. All right, so it doesn't look like it's one of these product things here for us. So on the back, integer powers of sine and cosine. We see that Roman numeral 4? Super. So we're looking for cosine cubed. What number formula is 1 over cosine cubed is which one? Is 21, right? Not up here at 18, but 21. How do I know I can't use 18? How much is n? for number 18? Would be -3, right? Because we got to get it on the bottom. But if you look all the way at the end of formula 18, what does it say? N has to be positive, right? So you got to read the fine print sometimes. Okay, so we are applying formula 21. What's the bad news about the right-hand side of formula 21? There's another integral in there. So it's not going to be a straight, we're not going to be just done. This is a trade, right? We're trading one integral for hopefully one that's simpler. Okay, so again, we'll need somebody to help me out here. This was formula 21, right? Okay, who's got an answer for me on this one? Steve. Okay, so can somebody confirm that? I'm relying very heavily on you guys for these formulas. So that looks okay? Okay, so we've traded 1 over cosine cubed inside of an integral for 1 over cosine, which seems better, right? That's an easier thing inside of the integral. Yeah, so the integral of 1 over cosine, I think, is another formula in our list. It's number 22. See it? Great. So sometimes one formula will lead into another. This guy right here is formula 22. And so I'm just going to copy all the beginning stuff. Yes. Yeah, so you probably don't want to write it as cosine to the -1. It's fine to write it that way, but it would be confused with inverse cosine. Yeah. Well, it's really that the -1 is, we're asking too much of that -1. Sometimes, almost all the time, -1 means inverse of some flavor. A particular flavor is this multiplicative inverse, right? That's what we think of as a power. But that -1 really just means inverse in general. And so it's tough when we use inverse to represent, we use that -1 to represent inverse there, F inverse there. If you guys know anything about like a matrix can have an inverse. So we use -1 generally for inverse, but we kind of ask it to do like double time as a power up here. And so that's why it can be tricky to use it in 2 different ways. Okay, so I'm copying here plus 1/2. All right, now I need somebody to help me out with formula. Another 1/2, you said? Yep. Okay, you can put the plus C inside. I'll stick it on the outside. Questions on that one? Absolutely. Yeah, you can merge those halves together to a quarter. Probably should. Other questions on this one? All right, let's take a look at part C. Sine to the 4th times cosine cubed. Again, we've got powers of sine and cosine, so it feels like it's going to be somewhere near the formulas we've been looking at. Anybody find any candidate for sine to the 4th cosine cubed? 23. All right, so 23 has a whole paragraph of stuff written about it. But 23 is the right pattern, right? How much is m and how much is n? How much is m? 4 and n is the 3. Okay, so let's see. So I've got m is 4 and n is 3. And then it makes us read some stuff. So let's read some stuff. So it says if m is odd, okay, is that true in our case? M was 4 in our case. No, so I'm not even gonna read the let. I just stop reading that sentence because m is not odd. If n is odd, is that true? Yes, because n is 3. Okay, great. If n is odd, we're gonna let w equal sine of x. What is w? W is the u that we've been doing for u substitutions. They call it w. but they are saying use a u substitution with u equal to sine of x. That's the only hint that we get. The rest of this is also not true if both m and n are even, which isn't true, right? Okay, so we don't need to read anything else. The only help we get is that n is odd, so we're going to do a u substitution with u equals sine of x. And apparently something good is supposed to happen. Then you can do either one. Okay, so let's give our u substitution a shot. What did it say? Sine or cosine? Sine of x. So u is equal to sine of x. So du is cosine. And then let's see if we can start rewriting our integral. So integral equals, okay, instead of sine to the fourth of x, what are we putting? U to the fourth. Okay, so we get our u in there as painlessly as possible. And then we're underlining everything else. So what's everything else? Cosine cubed of x dx, and we're trying to build that from here, which doesn't seem very promising. So how about we do this with a slightly different perspective? How about we say, well, I have a cosine of x dx that I can rewrite in terms of u, right? So I'm going to think of that cosine cubed as really being cosine of x dx times whatever's left over. How many cosines are left over? 2 of them, right? So we're just taking that cosine cube, splitting it off because I have a very natural way to represent cosine of x dx, right? It's just du. Okay, so let's do that at least. So cosine of x dx becomes du, which means I still need to find a way to get that cosine squared dealt with, right? But cosine squared is part of a very famous trig identity. Yeah, we know that sine squared of x plus cosine squared of x is always equal to 1. And that's going to be the magic to finish this one. Which means that this cosine squared that I'm trying to replace is really the same as what? 1 minus sine squared, which is 1 minus u squared. That's the key, right? 1 minus sine squared, and then sine becomes u. So this is 1 minus u squared. And so that guy will come right in here. So it's a u substitution, but it's another one of those kind of weird ones where it looks like it's not going to work, right? You do whatever you can do, you get your u in there, you get your du in there, and you hope there's really no other variable left. Turned out there was. We still had cosine squared of x, but then through this trig identity replacement, we were able to change that into something with u. Do we want to see the end of this one, or can we move on? Right, distribute that u to the fourth, and then it just looks like an ordinary polynomial with the power rules. Okay, so all right, so you want to change it to instead of a 3, you want to make it okay, so 8. We were in the odd case here, so give me an odd number. 9. Okay, suppose that we have cosine to the 9th. So we're still peeling one of these cosines off, because that's still going to be part of my du. So how many cosines are left over here? That's now 8 of them left over. Cosine squared we can raise that cosine squared to the 4th power, right? And that's our 8 of them. And so this guy is to the 4th power. And so it's a little bit annoying. You have to distribute 1 minus u squared, but it's still just a big old polynomial. And I think Aaliyah made a good connection there about that's why it has to be odd, right? We needed an odd number of cosines so that when we pulled one of them off, we had an even number of cosines, which allows us to use this cosine squared identity. I think we can only really use one of them in terms of getting absorbed in the du. Like that du needs to make its way into the integral, and that involves a single cosine. So whatever's left, we have no control over. Yeah, good question. Okay, so we're not going to finish this one, but we are going to move on to the next page here. Okay, number 3 says sometimes we need to do a U substitution to get our integral into a form that's in the table. So search as you might, you won't find anything that looks exactly like this mess right here. E to the square root of x sine of 2 square root of x over square root of x. It's just way too particular to appear in our table. So let's try doing a U substitution, and we'll cross our fingers. Natural thoughts or choices for you? How about the square root of x? It's the thing that's up on the power. Another perfectly good choice would be 2 square root of x, the thing inside of the sign. You could just pick one. I think either one would work just fine. So I will tell you this. I have taken the derivative of the square root of x so many times that I just know what it is without thinking of it as x to the half and then going through that power game. So I'm just going to jump to the answer here. It's 1 over 2 root x. And say if you're willing to just like know this, then you're going to save yourself a lot of hassle. Not just hassle, but if you had written this guy as a 1/2 x to the negative 1/2, you might not recognize that this piece of the du is exactly right there, right? Like I see it because I just automatically write it as a 1 over square root of x with the 2 in the front. All right, so let's start changing our integral. I equals integral. Okay, that guy becomes e to the u. Wonderful. The next thing becomes sine of 2u. Yeah? It's not a coincidence that the square root of x is part of both pieces. That is a 2u. And then I will underline what's left. I've got a square root of x on the bottom and a dx. And I can see that right there, which means that 2 on the bottom is not part of what I want. So we get it out of the way by multiplying both sides by the 2. So that thing in the box is really equal to 2 du. And by that, I'll write it separately just so we see it. Yeah, just a big 2. So this tells me that 2 du is exactly the thing that I want. Let me just underline this first. Okay, so Rob says, well, what if we decided to recognize that this square root of x right here is exactly u? And that means you can put, right, we could have just put an over u here. Okay, so first of all, does an over u there make the integral easier or harder? Harder, right? Like more stuff in the integral is generally not a good thing. But more important than that, if you decide that this square root of u is actually just going to, sorry, that square root of x is just going to become a u, then there's no way for us to get our dx, like there's no way for us to get the du into the integral, which I haven't put in here yet. Oh, sorry, yeah, it's right there, 2 du. We have to, like the priority is to get the du in there. And so whatever the du needs to have, you got to give it to it first priority. Yeah, and then whatever's left hopefully can get changed into u's. Okay, I can ignore that too. It's a constant multiple. I'm envisioning it in the front. E to the u, sine of 2u. Now we look at the table. And again, start with the bold. Don't read every formula. This is the product of an e thing with a sine thing. And I think there's a whole section of products of e's and sines and cosines, right? Whole section. So have we found the formula? What number is it? Number 8, e to some stuff, sine of some stuff. There's the formula. Wonderful. So very carefully apply that formula, write down your answer, and then the last step for this one would be to get rid of those u's and go back to the x's. Yes, you could. If it was a definite integral, we would want to switch those limits. Exactly the same answer. All right, so if somebody can look up at my answer and tell me whether or not I got that right. Yep, definitely want to put that 2 in with the 1/5. Are my pieces all in the right spot? There are a lot of parts to these guys. So yes, you have no choice for A. A is 1 because the formula says e to the a times x, but we have a times u. Yeah. So a lot of mental hurdles to kind of change the letters that you have into the ones that are on the page. All right, so A is 1, and how much is B? Is 2. And so then it's just a matter of copying that formula out. All right, and then I'm just going to change all of these u's into what? Square root of x. So I'll be lazy. Don't be lazy. And I'm just going to cross them off. Yeah, just another parentheses. Any questions on that one? 1 times sign. I just put the 1 in so we would see that was the A. Questions? Okay, so we're going to look at number 4, which has 3 different parts. And before we get into the nitty-gritty details of number 4, I just want to compare the 3 original problems. So the first one is this integral 1 over x squared minus 8x plus 15. Okay. The next one is x squared over the same thing, right? And then the last one on the next page is 1 over x squared minus 8x plus 18. I think it was a 15 a moment ago, right? Slight differences in these 3. It's going to turn out the solution method is very different for the 3. All right, let's go back to part A. Okay, again, looking for something in the table that has a chance at matching this guy right here. So what we've got is a polynomial in the bottom. Any of these things look like polynomials in the bottom? Yeah, look at section Roman numeral 5, which says quadratic in the denominator. You see those? Which is exactly what we have here, is a quadratic in the denominator. So the first one, the denominator is x squared plus a number squared. Is that this? No. The second one is the same kind of denominator. The third one and the fourth one, 26 and 27, the denominators are factored. So apparently, if you can factor the thing, you have a door, right? You have a way in. So what should we try to do? Factor. Okay, so let's factor this guy. Okay, so hopefully we have a -5 and a -3. Now it makes no difference what order you put them in, but can you just copy the order I put them in? If you swap them, just put them in my order just so we're all looking at the same thing. Again, doesn't matter if you swap them, but let's all talk the same language here. Okay, which formula are we looking at? What number? 26, that looks good. 1 over something factored, okay. So follow all the pieces and see if you can fill in with formula 26. How much is A in our example? Is it -5? It's +5. Notice there are minus signs built into this formula. So A is 5, B is 3. So many of the formulas that we are just kind of blindly using right now are either involve techniques we've just seen, like some of these are integration by parts problems, or techniques we're going to see right after the test. There are, yeah, I mean, every one of the formulas on this page came from some technique. We've seen some, we're going to see some more. Yeah. Okay, so I think we're good, right? Just change that first fraction to a half and we've got our answer. Questions on this one? Okay, part B, what's the only difference? X squared. Okay, so maybe the table can help me. So what's going on near the table with 27? How about 27? It's not x squared. It's a linear thing upstairs on 27 instead of a quadratic and x squared. Okay, so we can't use that. You can look around on the table. You won't see anything else that looks good either. So here's the goal. The goal is to turn this thing into something that looks like 27. Right now it's an x squared on top, but I want a linear thing on top. All right, so we're going to do some division here. What we need to do is long division of polynomials. So it's probably been a while since you've done long division with numbers. It may have been longer, if not forever, with polynomial long division. Let's give it a shot. I think this is probably something we do in our college algebra class, 107. What other part? This is the setup for the long division, and now we got to do the process. So here's the process. We're going to take this guy here in the front, and we're going to divide it into this guy in the front. So this division happens to be easy. How many times does x squared go into x squared? Once, but because they're the same, I just want to put some arrows here so you know which one is which. It's the guy in the front is going into the guy inside. And we say, oh, super, that goes in exactly one time. So once, I'll put, I don't know where, I'll put the one up there. And then after you figure out how many times the thing goes in, what's the next step for regular long division? Is you multiply, right? You take that one and you multiply it by the thing that was in the front. Okay, so then we're going to multiply. So 1 times that stuff over there is x squared minus 8x plus 15. Just making a note so you can check it out later. This is 1 times the whole thing in the front. Still remembering long division with numbers, what's the next thing after you have that written below? Is we subtract, right? Top guy minus bottom guy. I'm going to put minus and then parentheses. It's top minus the entire thing. What happens with the x squareds? They cancel, and if they didn't, it means we made a mistake. We built it so that those x squares would cancel. And then we're going to subtract the rest, minus 8x plus 8x, because there's an invisible 0, x is up here, minus negative 8x, that's plus 8x. How about this 15? Minus 15. Everybody see that negative distributing? Okay. And if there were numbers, if this were just a straight number long division, then we would do our next division. We would take the x squared and divide it into this new 8x minus 15. Maybe if there were some other number here, we could bring it down, right? Okay, but x squared doesn't go into 8x. There's not enough x's inside of the 8x. X squared has more x's in it than 8x does. And so we're done with the long division. And when you're done, this guy at the end has a special name. It's called the remainder. So that 8x minus 15 is the remainder. So let me write down a pure like pre-calculus / algebra fact, and then we're going to come back and do the calculus. So let's put it right up here, actually. Okay, so here's what we just discovered, is that the original integrand, x squared over x squared minus 8x plus 15, is exactly equal to, how many times did the outside guy go into the inside guy? Once, plus some remainder. What was the remainder? 8x minus 15, but it's a remainder out of a certain like whole. What was the whole? Is that x squared minus 8x plus 15. That's what we just discovered. And if it's, yeah, and if you need to like put some numbers in there later on to just remind yourself, yeah, that's where the pieces went when we did regular old long division, then you should do that. And I'll try to share with you, like in advance, hey, here are the techniques that maybe you haven't used in 2 years that are now fair game because they make it so we can do some integrals. Okay, so we did the long division. Now it's time to do the calculus part. Instead of integrating the original, we're going to instead integrate this 1 plus 8x minus 15 over, right? They're both exactly the same. So then I'll put over here my integral equals. So I'm just going to be lazy and imagine an integral sign on top of this thing. So what's the integral of 1 dx? Is x. Okay, great. So the first guy becomes an x plus, now I'm imagining, I'll put it here and then I'll erase it, but I'm imagining the integral on that thing, which is a formula. That's formula 27, right? So now we just apply formula 27 and it's done. It is on the 1. I've already dealt with the 1 plus. That's the x that I put over there. Levi. Okay, so very carefully follow the formula from 27. So. Oh, there's a lot of pieces here. Okay, so what do we have at the beginning? 1 over how much? It's the same 5 and 3 that we had before. All right, and I'm bailing out. I can't do this in my head anymore. So I'm just going to write down what the values of A, B, C, and D are. A and B are the same 5 and 3 that we had on the previous problem. C and D, what are they in this problem? 8 and not 15, but negative 15. And then we're just going to plug in. And so as things get more complicated, there's no shame in writing out here's what the letters are and then using the formula. So if I did it right, my first term there is a 0. Did I do that right? Did not do that right? Oh, I did it wrong. Five times 8. Thank you. Wait, 5 times 8 or 3 times 8? AC plus D. 5 times 8. Second one is BC plus D. 3 times 8 plus negative 15. Okay, I'm ready to move on. Any questions on this one? See, you woke up this morning having no idea you'd have to do polynomial long division in your calculus class. All right, Eli asked about like all these algebra techniques. Do you guys remember completing the square? It's time. We're going to complete the square on part C. So the problem with part C, what's the first thing we did on the denominators before? We factored. Okay, can we factor that denominator right there? And the problem is we can't. We can't factor that denominator. But that's the first thing to try. Turns out if you can't factor it over the rational numbers, then completing the square might work instead. So let's complete the square. X minus 8 times x. Yeah, so So only if we can get it into factored form, so it looks like the table. And I think that plus 18 is not workable. Like we just can't get around that. Okay, so here's what we're going to do for completing the square. I'm going to copy my original denominator. I'm leaving a little space in the blank there. We're going to fill that in with some magical number that's going to make this all work. So do you guys remember, like for completing the square, like this guy right here is the b. Right, that's your b. And there's some magic formula that tells you what you're supposed to put in here. You'll see. Anybody remember the magic formula for completing the square? B over 2 squared. What are you reading from? Man, Alex is preparing his notes from pre-calc. Okay, so yeah, so we're going to take that guy, we're going to cut it in half, and we're going to square it. And that's the magic formula that works for completing the square. So I'll put it down here. B over 2 squared is always the right thing to put in that blank. So let's find it in this case. So half of b is -4. We square that, we get positive 16. So right in here, we're going to put a plus 16. And then right away, I mean, I can't go around arbitrarily adding 16 to things. So right away, I'm going to subtract 16, right? So I haven't cheated. So it's equal to what it was before. But now I'm going to choose to group things differently than they were before. I'm going to group these guys together and then whatever's left over. And if I just look at the first three terms, x squared minus 8x plus 16, that you can factor. So take a moment to factor first three terms, x squared minus 8x plus 16. How does it factor? Is x minus 4 times another x minus 4, which is x minus 4 squared. And then plus 2 is what's left over. Mm-hmm. And plus 2 is the only number that will work for this guy. But to make it a perfect square, I mean, you might be able to factor it in different ways, but we need it to be a perfect square for reasons that aren't clear at this moment. Okay, so we factored, we completed the square, and now it looks like x minus 4 squared plus 2. Okay, I'm looking back at my sheet. Okay, so it's not 26 or 27, right? Because in 26 and 27, it's just straight factored downstairs, and that plus 2 is no good. But if you look at number 24, number 24 has a 1 over x squared plus a squared, right? In your mind, that x could have come from some u substitution. So really, it could be 1 over u squared plus a squared, right? 1 over anything squared plus a number squared. And that's what we have here. So first, I'm going to rewrite my integrand. 1 over what we built, x minus 4 squared plus 2. And then we're going to do a u substitution. This will be a very easy u substitution. We're going to let u equal the x minus 4 in the parentheses. What's du? Just dx. Yes. No problem. We can. Okay, x minus 4 becomes u, so this guy is our u squared. That plus 2, I'll just leave it as a plus 2, although a couple of folks see where we're going with that guy. Dx becomes just du, right? Pretty straightforward u substitution. And now, fortunately, it looks just like 24. 24 is supposed to be 1 over the variable squared plus a number squared. That 2 is what number squared? Square root of 2. So maybe I'll just erase it and write it the way I'm thinking of it so that it looks like the formula. It's supposed to be some number squared, no problem. It's the square root of 2 squared. Okay, so now we're doing formula 24. So 24 becomes 1 over square root of 2 arctan u over root 2 plus the c, and then change that u. So the hint is right below what's on the screen. So we're just going to pause for a second and then we'll look at the hint. Right, so last step, just change the u into an x minus 4 and it's done. Questions on this one? Okay. Alex, can you read number 5, please? Okay, so let's pause and make sure we see that's exactly what we did in these 3 cases. What did we do to the first denominator? Because we just factored, and that was fine. And the second guy, what did we notice? Whoops, part B is down here. What did we notice about the degree on top and the degree on the bottom? Yeah, the degree upstairs was greater than or equal, which means if you do long division, you'll end up with something less than the degree downstairs, which opened us up to one of the formulas in the table. And then finally, if you cannot factor it, the fancy word is irreducible, then you try completing the square because maybe that looks like formula 24 or 25, I think. Okay, so to be clear, you will not have this table of integrals in front of you on the test, but I will ask you one question on the test where I want to see if you can apply a fancy formula. And so I will provide for you any fancy formulas that you need. I actually think I'll probably give you like a partial printout or something of the formulas. And yeah, the one you need will be in this list, but I'm not just going to say use this formula, right? Okay. Too much. All right, group activity starts on the next page. Just to be clear here in terms of answers. So if you really don't know how to get started, if you go after the activities, you will find hints to each of them, and then you'll find the answers. So you don't need to just jump to the answers if you're stuck. You could at least look at the hints in the intermediate.